morning to everyone. A warm welcome to today's webinar on radio frequency measurements for cellular and wireless communication systems. So it is the 5:15 to 5:30. It is a protocol 15 minutes, and then the speaker will speak at 5:30 p.m. onwards. It will take up to 7 to 7:30 p.m. Then the interaction session will be begins. I request all the members except officials, please mute yourself, either audio and video also. I request all the participants, please mute yourself, video and audio. It is a humble request from organizers. Please mute yourself except college officials. All the participants are requested to mute yourself, both audio and video. So today's webinar delivered by Dr. Ramakrishna Y, Senior Member of Technical Staff, Lightpoint Corporation, USA. Now I request our Principal Dr. P. Ravindra Babu Garu address on this occasion. I request Dr. P. Ravindra Babu Garu, please your address words to our all participants. There is 100 participants are in this session. Sir, Principal Garu, please proceed.
Can I speak?
Yes, sir. Yes, sir. Please proceed.
So, good evening, everybody. I welcome you all to this webinar. I welcome Dr. Ramakrishna Y from USA, voluntarily came to give the webinar. I am very happy to see all of you. I hope that all the members of our family are in safe mode in COVID-19. As far as the college is concerned, established in the year 1998, I'm very happy to say that we have completed 4th cycle of NBA. I'm very happy to say that our Electronics and Communication Department completed 4th cycle under Tier 1. So that is the status. We are working as a team. I welcome all the faculty members and other participants from the other colleges. Especially the need of the hour is academic expansion, excellence and innovations. The order of the day is to meet the expectations from the higher education, especially to meet the industry 4.0. The 4.0 is Internet of Things, machine learning, big data analysis. I like that. So I request all of you, please take this as a challenge. This is one topic we have initiated. Take this as a challenge and proceed with the help of our expert, Ramakrishna Garu. I wish you all the best. Thank you very much.
Thank you, sir. Thank you, Principal Garu, for your words. Now I request another two officials in the Good Level Air Engineering College, Vice Principal Academics, Dr. GVSNRV Prasad Garu, another Vice Principal Administration, Dr. P. Karunakumar Garu. Now the Vice Principal Academics, Dr. GVSNR Prasad Garu, please address the gathering.
Good evening, Andy. Good evening, Ramakrishna Garu, and I'm very much happy to see in this occasion. And this is a good initiative by Department of Electronics and Communication Engineering. And this will help the faculty members to gain the knowledge in a particular area. So it's a good initiative. Thank you very much for the organizers to give me this opportunity. All the best to all the participants. Thank you, sir. Thank you. Bye.
Thank you, sir. Thank you for your encouraging words. Now I request Vice Principal Administration of Good Level Engineering College, Burra Karunakumar Garu, will address and best wishes for us on this occasion.
Sir, mute chairman, unmute chairman, sir.
So, thank you, sir.
Yes,
Respected Principal Dr. Ravindra Babu Garu and today's resource person Dr. Ramakrishna Garu and my dear colleague friends, I am very happy to be a part of this inaugural session of this prestigious webinar. Always it is desirous to have advancement of the knowledge or to have inquisitiveness, to probe into the technical complexities. For that, the faculty should be empowered with the cutting edge technology and more interaction should happen among the faculty friends. I am sincerely thankful to the Department of Electronics and Communication Engineering for choosing a very good topic for the purpose of the webinar, and the cooperation and guidance accorded by the speaker, Dr. Ramakrishna, is highly appreciated. And I advise all my colleague friends to make use of this opportunity and to probe into the various aspects of the topic and to take it further in the days to come. Thank you, everyone. Thank you, sir.
Thank you, Karunakumar Garu. Thank you. Now I request Dr. VVKD Prasad Garu, Head of the Department of Electronics and Communication Engineering, Good Level Engineering College, address the participants.
Thank you, Professor Kamraj Garu. Sir, am I audible, sir?
Yeah, yeah.
Sir,
Yes, please proceed.
This is Dr. VVKD Prasad, Professor and Head of the Department of EC, Good Level Engineering College. Respected Principal, Professor P. Ravindra Babu Garu, and respected Vice Principal Academics, Professor G.V. SNRV Prasad Garu, and Vice Principal Administration, Professor B. Karunakumar Garu. Man behind this webinar, my friend Professor M. Kamaraj Garu, and today's resource person, very eminent personality, Dr. Y. Ramakrishna Garu, other professors and participants of this webinar, good evening one and all. At the outset, I extend my warm welcome to all of you to this webinar on radio frequency measurements for cellular and wireless communication systems. We know there's a lot of difference between theoretical concepts and their practical implementation. So unless we fill up the gap between them, our knowledge is not complete. Today's topic is related to this. Practical aspects of radio frequency measurements for cellular and wireless communication systems. It is very fortunate to have such a eminent personality, Dr. Y. Ramakrishna Garu, with us. Thank you very much, sir, for sparing your valuable time for associating with us to enlighten us. And also congratulate on this occasion Professor M. Kamaraj Garu, who planned and organized this event, and Vishendra Babu also, who gave technical support. Now I request all the participants to participate actively in this webinar and get maximum benefit out of it. And also request the participants, if you have any doubts or questions, queries like that, you please ask at the end of the webinar, so that in the middle the webinar will not be disturbed. Now I request Professor Kamaraj Garu to continue this session. Thank you, sir.
Okay, thank you. Thank you, Prasad Garu. Now a brief introduction. I'll tell you one thing. I asked it to submit the detailed biography of Ramakrishna Garu, today's speaker, but he said immediately, Sonta Dabba Oddu. So just I'll give 2 lines, then just read out. That is also not necessary. So that is an indication of a simplicity of a man, an engineer. Ramakrishna Garu accepted our request immediately, voluntarily, and delivered it up for all our staff of EC department as well as the other colleges faculty also. The biography may be very like this. The Ramakrishna Ellapantula works as a senior member of technical staff at Light Point Corporation since 2010, overseeing wireless technology solution for his company's products. Previously, Mr. Ramakrishna worked for Motorola for 13 years, developing wireless 3G and 4G technologies. And RK received BE from Andhra University, MBA from University of Chicago, and prestigious PhD from University of Illinois at Chicago. He currently holds 7 US issued patents and have numerous publications. So the simple man, also its biography also seems to be simple, but at the same time, achievements or maybe credentials are more. Thank you, Ramakrishna Garu. So now it is as per our schedule. The time is 5:27 now. I request speaker Dr. Y. Ramakrishna Garu to hand over the session. Before that, I thank our principal Dr. P. Ravindra Babu Garu and Vice Principal Academics Dr. G.V.S. Annavaru Prasad Garu and Vice Principal Administration Dr. B. Karunakumar Garu and my friend Dr. V.V.K.D. Prasad Garu for joining us to inaugurate today's webinar. I request speaker hand over the session. Thank you, sir. Thank you, Anand.
Yeah, good evening, everybody. Namaste,
evening.
first of all.
Good evening, sir.
Thanks for the opportunity to speak in front of all the humble and very respected personalities of GEC College of Engineering. And I would like to thank the principal, vice principal, the head of the department, and of course, my very good friend, Dr. Kamraju, for giving this opportunity to say a few words about my experiences of working in cellular and wireless area for the last 23 years. So, done with that. So what I'm going to do is first, I also hope, everybody is safe and health-wise and otherwise because of this virus pandemic. And I urge you to take care of yourself and your families, and we will get through this.
Thank you.
Okay, now that it's done, let me, what I'm planning to do today is, I would like to obviously talk a little bit about the RF measurements and wireless communications and cellular systems. Also, I think it would be good if I were to talk, take a few minutes to talk about my company, because I think that's where the industry versus, the theoretical aspects and how my company is bridging the gap. So we'll take a few minutes and we will talk about my company as well. And like Dr. Kamraj requested, if you could hold your questions until the end of the seminar, then we could try to answer all of them. And a better way, in case if you forget, if you have a question, if you forget, a best way is to type it up in the chat. So at the end of the webinar, I could scroll through the chat and go through the questions one by one. Maybe you can put your name and type your question there, and that way nothing will be forgotten. All right, let's go to the presentation now. I hope everybody can see the screen here.
Yes, sir. Yes, sir.
Okay, very good.
Proceed, sir. Proceed.
Okay, thank you very much. So, okay, this is the obviously the starting of the the slide header. So Dr. Kamraj already explained, but very quickly, I worked at LightPoint Motorola before I am at LightPoint Corporation. Before that, US Robotics, PhD from the University of Illinois and MBA from the University of Chicago, and some patents and some publications. Okay, let's move from that. So what I would do is, this is the agenda today. We'll talk about the baseband and RF communication systems, some of the modulation techniques, impairments, measurements, examples, and summary, and finally we'll take the questions. So you may, coming to this webinar, you may expect that I may be covering something very complicated, but no, we'll be covering extremely basic topics actually. Very, very basic. Modulation, single sideband modulation, double sideband modulation, and how that relates to even the latest smartphones that we use today. It will be very helpful to see that whatever that we studied in our BE, in our undergrad, is something that is still being used to develop the latest technology smartphones. So I hope that this webinar is going to give you an idea on what happens before a cell phone is manufactured in the factory, and before you use it, what are all the different things that goes behind it. So having said that, very quickly about my company. So LightPoint Corporation is part of a bigger company called Teradyne. It is based in Boston. LightPoint is headquartered in San Jose, California. And I work at their branch office in Arlington Heights, which is about 30 miles north of Chicago, Illinois. So LightPoint is a very small company, actually. It was founded in May 2000, about almost 20 years ago. And then in October 2011, we were acquired by Teradyne for about $600 million. So these are some of the products provided by Teradyne, chipset solutions, subsystem solutions, and final product test that includes the LightPoint division, and then material handling and all the things like that. So this is all the product portfolio of Teradyne, and here is LightPoint. Okay, we are a small part of the much bigger company, Teradyne. So this is the footprint of LightPoint. We are located pretty much everywhere in the world, and mainly in China. And because most of the manufacturing until now is done in China, we don't know what's going to happen going forward, but for now it's in China. So that's the reason why we have a pretty strong footprint in China and other places of the world. So again, like I mentioned, we are wireless for everything. The respected principal was mentioning about IoT and wireless of things. Is the future to come. We play in that role. Wireless infrastructure, like your at-home gateways and Wi-Fi boxes and everything, we play in that space. And of course, laptops, smartphones, tablets, we play in that space also. So these are some of the solutions offered by LightPoint in different technologies. When I say cellular, we're talking about cell phone. Connectivity is more of a Wi-Fi. And the navigation is GPS and all the things like that. So we play in 3 different spaces. As you can see, we have footprint in every possible wireless technology that's out there. So I'm going to skip all these slides. Basically, what I'm going to do is I'm going to just, why somebody has to test, what is the point of testing? And that is something we are going to be learning in our webinar. When I say testing, I'm talking about RF testing. What is really RF testing? You take the measurements of a device and make sure those measurements are actually in line with the expectations. And then before you actually pack the product and ship it to the customer to purchase, you test it and make sure that the measurements and everything are in line. And so basically, these are some of the products that we offer in LightPoint. And again, like I said, Wi-Fi and connectivity is this one, cellular, IoT, and the millimeter wave. Millimeter wave is the latest 5G NR technology that is coming in. So, okay, enough of that. Let's move on. All right. So again, let's take. Most of us are pretty senior here and experts in our respected areas, but let's take a step back to our BE, our undergraduation. We learned about analog communications and digital communications and things like that. So we're going to start our webinar there. So a baseband communication system basically means there is no RF, there's only the baseband. If anybody remembers the old day modems, that's the telephone modems, that is an example of a baseband communication system. So that means there is no radio frequency there. You connect your phone line to the laptop, and then you dial a number, and then you establish the internet connection. That is more like a baseband communication system because it's operating only at the very, very, very low frequencies. So that's what a baseband communication system is. It transmits this baseband signal over a low pass channel. Some of them are ADSL, cable modems, and things like that. And obviously, when we transmit a signal, there are a lot of errors in the signal, right? There are some of the errors of the channel, the noise, and the analog to digital converters and digital to analog converters. And they also have something called a clock. The clock also changes, over time because of the temperature, humidity, aging, and all those reasons. So what are the pros of the baseband communication system? It's very simple to implement. There is no RF in there. You just take a signal, you modulate it to whatever you want, and then you send it over a telephone line, and then on the other side you receive it. Okay, so it is because of it's a very simple to because of that it's very simple to implement, and because there is no RF. Okay, the signal to noise ratio of the channel or the telephone line is very high, so even reliable communication can be done at low signal to noise ratios. But what are the problems, or what are some of the disadvantages of baseband communication system? They're band limited. When I say band limited, again, I take you back to a few years, some maybe 10, 20 years ago, when we had a modem at home, a telephone modem, the maximum speed is about 56 kilobit per second. That's what I mean by band limited. Now, if you look at your typical cell phone, you are downloading data at 100 megabit per second, 200 megabit per second, see the difference, 56 kilobits versus 100 megabit. So baseband communication systems, while they are simple, they are bandwidth limited. You cannot really pump a lot of data into those baseband communication systems. And they are wide line. That is the other thing. Remember, again, I'll keep going back to the past because that's where we think we forgot, but that's where most of the technologies in developing a phone and all is actually there right now. So in the wide line, I remember I came to US in 1994 to pursue my higher studies, and then we don't have a phone at home, a telephone. So I asked my dad, can you please have a phone at home so that I can call you once in a week? It took him about 2 years to actually get a telephone at home. And because it's a wide line, somebody has to put a line, a wire from the exchange to the house or whatever it is. Imagine a cell phone. I can go to the store right now and I can pick up a SIM card in 1 minute. So that's one of the disadvantages of baseband communication system. So because of that, it's not easy to scale or deploy. It means if I want to have a communication system in some certain place, somebody has to go there, put the wire and all the things like that. So let's keep that in perspective, right? Although they are very simple to implement, very good signal to noise ratios, one can really communicate even at a low SNRs, there are significant drawbacks that will limit their usage. All right, let's take a deeper look into what a baseband communication system is, and then we'll scale this up to the RF communication system.
Hey, how's that?
Okay, so basically you have the data coming in, the digital data, and that data actually goes through some kind of channel coding, and like Viterbi coding, turbo encoding, and things like that, and then it goes through a modulation like QPSK, 16 QAM, 256 QAM, and then that digital data has to be converted into analog form before it can be transmitted. So that is what digital to analog converter is, right? And then we transmit that using a TX filter. Why a filter is needed? The filter is needed so that we limit the spectrum of the transmitter signal. Otherwise, there'll be spurious emissions. There will be leakages to the other parts of the spectrum. Therefore, the transmit filter is needed. And then the signal is transmitted over a telephone line. We call it a channel, okay? And so this is where the central exchange is actually transmitting the internet data, for example. And here is our user. Our user receives the data over the telephone line, and it's corrupted by the noise, additive white Gaussian noise. And they also have a similar matching RX filter. Okay, again, it's not very clear to see, but it's about minus FM to plus FM. Okay, that's a frequency range. Okay, and then that analog signal is going to be converted into digital form, analog to digital converter. And then there are timing corrections that are done. Why the timing corrections are done? Because if you look at it, digital to analog converter has a clock, and analog to digital converter has a clock. And these two are not in line with each other, or they're not synchronous to each other, because this is an independent entity and the receiver is an independent entity. The transmitter is an independent entity, the receiver is an independent entity. Because of that, we have to do the timing corrections. Okay. Once we do the timing correction, whatever the modulation is done here is going to be recovered. Whatever is the coding is done here, that is going to be recovered by channel decoding, and the data is out. The hope is that whatever is the data that is sent here is the same data that has been received here. So we could download a video, or we can, look at a web page or whatever. So here I'm kind of showing source of controllable errors, source of uncontrollable errors. What does that mean? Let's take about the source of controllable errors. So digital to analog converter, let's say it's operating about 10 megahertz frequency, the clock, okay? And I did discuss before, these clocks have, because of the aging, means I manufactured the clock today, and a year from now, it became a year old. Because of that, there will be some drift in the frequency. What does that mean? Instead of operating at 10 megahertz per second, it will be operating at 10.1 megahertz per second, or maybe 9.99 megahertz per second. Okay, or because of the temperature, if there is a lot of, we're talking about a place that is very hot or a place very cold, because of the weather also, hot and cold weathers. Remember, everything is inside the semiconductor. Okay, and because of the weather also, there will be a change in the base frequency, or maybe the humidity. I am from Visakhapatnam, and Visakhapatnam has extremely high humidity. Okay, because of the humidity, right? Then also the clock changes. So they call the tolerance of the clock. Means if the base frequency is 10 megahertz per second, how much does it change over time, over temperature, or humidity? Okay. Of course, I can have a 10% tolerance, means 10 megahertz is the frequency, the clock changes by 10%, depending on the factors. Means plus or minus 1 megahertz, means the clock can go from 9 megahertz to 11 megahertz. But that is a very, very bad clock. But the good thing is it's cheaper to manufacture. Okay. On the other hand, I can have a clock that is 0.01% tolerance. But the problem with that is it's going to be very expensive to make it, very costly in the production. So that's what I mean by source of controllable errors. What kind of clock are we going to put it here? What is the tolerance? How much price are we going to pay for the, this particular clock, right? Those are the source of controllable errors. Then source of uncontrollable errors, the channel and the noise. When I transmit the signal over a telephone line, correct? I do not know what's going to happen. The telephone line could be, very noisy, because there could be a crosstalk between one speaker to a different speaker. Or maybe there's a lot of noise in the receiver side, right? White Gaussian noise. So these are some of the errors that we're talking about, right? Again, I can control these errors in the clock frequency, for example, by paying more money, more cost, so that I can have a clock that is a lot more higher, tolerant than something that's of low cost. Whereas here, the channel, there's nothing I can do. That's the reason why the channel coding and modulation is actually used to take care of these uncontrollable errors. Okay. Now, we spent enough time on that. Let's move to RF communication systems. What is the point of RF? Again, like we talked about, baseband communication systems has these disadvantages, right? The hope is that with RF communication system, we hope to, get rid of those, disadvantages. So the main difference is we modulate the baseband at a lot higher frequency. So we are no longer on a baseband system. For example, the signal that I am dealing with right now at work, it goes at 39 gigahertz. The modulating signal is at 39 gigahertz. Just think about that, okay? And at home, the electricity that we have at home, it's about 50 hertz in frequency and 39 gigahertz in frequency. That's almost 10 to the power of 9 times higher frequency, right? That's how we modulate the signal. Some of the examples are cellular, Wi-Fi, Bluetooth. These are some of the examples of RF communication systems. So what are the source of errors? So when the signal actually leaves the cell phone and reaches the base station, it is propagating over the atmosphere, right? It could be raining. There could be a tree, you know, next to my house, or it could be snowing in Chicago. When I'm in Chicago, so we get about snow about 6 months in a year. It could be heavy snow, right? Because of this condition, sometimes we actually take our cell phone and we go out because we say that, oh, I'm not getting proper signal. I want to go out when we speak to our friends and family, right? So that's what I mean by propagation conditions, right? The atmosphere and the objects that are around our house, they act as a source of errors. And the noise, say I am speaking on a cell phone or a Wi-Fi or a Bluetooth. Maybe a good example is either Wi-Fi or a Bluetooth, and I have a microwave at home. The microwave and the Wi-Fi and Bluetooth, they operate at the same frequency range. So when I turn on the microwave and suddenly my internet speed drops, because the microwave is actually operating in the same frequency range, it is generating noise that is corrupting the Wi-Fi or a Bluetooth signal, okay? And then finally, TX-RX impairments, which is the whole topic behind this webinar. What are the TX-RX impairments? We're going to talk about that. And mainly we talk about the TX impairments, okay? So what are the pros, advantages? It's a wireless, that means it's a very, you know, easy to deploy. I can deploy anywhere, not band limited. What I mean by that, I could have the wireless RF frequency range, you know, unlimited, pretty much. You can, I mean, again, I'm using the word unlimited in a very broad sense here. Obviously, after certain frequency, the wireless signal will become light signal. So we are not really talking about that. But what we are saying is within the wireless RF spectrum, I could have a very wide bandwidth. And it's easy to scale and deploy, okay? And some other disadvantages, it's power limited. Means if I am very far away from the cell phone tower, that means my phone has to transmit with very high power in order to reach the cell phone tower. After some time, the phone does not have unlimited power. The phone's power is actually limited to certain range for many reasons. One of the reasons is to save the battery life of the phone, because the higher the transmit power, the lower the battery life, or the higher the transmit power, the bad is going to be for a human being, because they'll be holding the phone by the ear or whatever it is. Again, there is a debate in the science whether it's good or bad. We're not going to get into that, but let's say that some of the reasons, okay? And the transmitter and the receiver should be very precisely synchronized. Again, we talked about the clocks here, right? You know, that is not only the case, but there are more issues. We're going to talk about those things, okay? And let's look at, okay, I will go back here just quickly. You know, keep this figure in mind. I'm going to leave it for a few seconds. Keep this in mind. And then when we go into the RF communication system, you will see how this particular baseband communication system has changed. Okay, this is the baseband communication system. Okay, so obviously this is a transmitter and this is the receiver. Up is the transmitter, down is the receiver. In the baseband communication system, we have coding, modulation, D2A, TX filter, and then we have decode, demod, channel timing and correction, ADC, RX filter. So we have those in the baseband. But anything that's I kind of coded in blue, those are the new additions to the RF communication systems. So again, we do the coding, we do the modulation, we convert the digital signal into analog signal, we send it through a TX filter, and this is the actual up conversion using a mixer. You see here, this is a local oscillator, they call it, right? This oscillator runs at the same frequency as the RF frequency. So we take the baseband data, we mix it with a local oscillator at the RF, and we send it to the power amplifier, okay? And the power amplifier, after amplifying the signal, it'll send it to the antenna, okay? Then that signal from the antenna goes to the channel. This channel is actually now the wireless channel, okay? In here, this channel is a telephone line, for example, channel, a wired channel. Whereas here, the channel is a wireless channel, the atmosphere. Okay, and then let's call the receiver our cell phone. It has a receiver antenna. This is a low noise amplifier. It amplifies the signal and it receives the signal and amplifies it. And there's a mixer. So this mixer and this mixer are pretty much the same thing. They're operating at the same RF frequency. The only thing it's going to do is it's going to take the signal at the RF frequency and convert it down to the baseband frequency. Okay, a mixer. Then you have a receive filter and everything else we already know. ADC, channel timing correction, demod, and decode. Again, here I'm showing the source of controllable errors. We talked about the digital to analog converter clock, analog to digital converter clock. Here we also have a clock or a local oscillator in the mixer at the transmitter side, and we have a local oscillator in the mixer in the receiver side. These are the clocks that we can control by paying more higher price for it. We can get a lot more precise clocks, or whatever. So, and here is the channel, the propagation channel we call it. Okay, so this is the RF communication system model. Again, all these things that we studied back in the days, we are going there. And you may be wondering, why is this guy telling us about all this stuff? Because the fun part is going forward. Okay, let's see what's going to happen. Okay, so again, this is the building blocks. We already talked about that. I mentioned them. Okay, the mixer converts the baseband signal into RF bandpass signal, up conversion, or takes the RF bandpass signal into baseband signal, down conversion. There are some of the impairments. Okay, in industry we call impairments. We kind of polish the term, and we don't want to call them problems or errors. Would like to call them impairments. People like it. The engineers and scientists and all the researchers and everybody, they like to call them impairments. The frequency errors, phase noise, IQ gain imbalance, IQ phase imbalance, carrier leakage. We're going to talk about all these things. Okay, just keep in mind these are some of the impairments. Impairments are nothing but basically the errors or the problems where can things go wrong in this whole chain? Where can things go wrong in this whole chain? Okay, and we talked about the DAC, digital to analog converter, analog to digital converter. Some of the impairments are sampling clock jitter, sampling rate shift. We talked about that. We talked about the clocks, the tolerance, and the power amplifier. Okay, that is something that is a problem too. This power amplifier here, we know when a system is a linear system, when a input-output system is a linear system, we can model a lot of good equations, and we can model the system, and we can figure out ins and outs, the transfer function and everything. But if the system is not linear, the analysis becomes very, very difficult. Okay, very difficult. Most of the theory and background that we study, that becomes extremely difficult when the system becomes non-linear. Why am I talking about that? This power amplifier has a characteristics. At a low powers, this is a linear system. But as we keep increasing the power amplifier will become a non-linear system. For example, if I put a signal, a sinusoid at frequency F1 through a linear system, the output is going to be still at frequency F1. However, if a system is a non-linear system, let's say that signal is not only going through, but also just squaring it. It's a non-linear. Y equal to x squared is a non-linear transfer function. Y equal to x is a linear transfer function or linear function. If the signal that I'm inputting is y equal to x squared type, then basically I will, you can take a sinusoid and you can play with it. Basically what's going to happen is the original signal is going to be there, plus the harmonics. Like if I send F1 frequency, I'm going to get F1, 2F1, 3F1, 4F1, and so on and so forth. Okay, there will be harmonics generated. And same thing here at the receiver side, low noise amplifier. Even this is also, if I input a very, very high power signal, LNA is going to become nonlinear, and the output is not going to be the signal of interest, but a lot of harmonics. So that's what I mean by, impairments, intermodulation products due to limited dynamic range. They call them, in a very fancy term, there is intermodulation products. Means not only the signal of interest, but its harmonics. Okay, and basically these are some of the building blocks of RF and some of the problems and some of the behaviors. Okay, let's go back. This takes me back to 1990, I believe, in my second year, maybe 1991, my third year of engineering. Analog communication systems. Okay, it's AM, and we all think that we are doing this. So even now we actually use AM. Even in the digital systems we use AM, and we will see how. So for example, let's take a double sideband suppressed carrier modulation. Okay, so what does that mean? I take a baseband signal and I send it through a mixer. Okay, remember, this is the baseband system. The frequency is anywhere from 0 to f of m, and I have a carrier frequency f of c. Very I request the audience to please mute your speakers. Thank you. Let me see if I can find a way to mute.
I request all the participants, please mute your voice and video. Nagaraj garu, మీ ఫోన్ మ్యూట్ లో పెట్టుకోండి. సార్ నాగరాజు గారు మీ మ్యూట్ లో పెట్టుకోండి మీ ఫోన్ ని.
Just a second, let me see if I can find
I request Ramakrishna garu, please mute all the everyone except me. Please mute everyone, please accept me.
Okay, I muted everyone, sorry about that. Okay, let me see if I can share the screen again. All right, so can Dr. Kamraj, can you please tell me if you can see my screen?
I'm seeing your screen.
Okay, thank you. Okay, thank you very much. Sorry for the trouble. So basically, let's go back to DSBRC, double sideband suppressed carrier modulation. Okay, some of the pros are very simple to implement, low equipment cost, but the disadvantages, the cons, is the poor use of the spectrum. Okay, and so what is it? I have a baseband signal, I have a carrier. Typically, the carrier frequency is a lot higher than the baseband signal frequency. I send it to a mixer. So basically, this is what I'm going to get. I'm going to get the same, exactly the same baseband signal, which is at 0 frequency. Now it is shifted to the carrier frequency, f of c minus f of c. Okay, and then I have the upper sideband, lower sideband in the positive frequency range, and then on the negative frequency range, I have exactly the same image. Okay, and this is a very simple equation. We all studied this. Okay, but what, it's very simple. All I have to do is take a baseband system, a signal rather, send it to a mixer, and I got this. But what is the problem with this? So if you look at it, upper sideband and lower sideband is as if there's, if I put a mirror right in between, and USB is a mirror image of LSB, LSB is a mirror image of USB. So that means I'm unnecessarily wasting 2 times the more spectrum. For example, if it takes about f of m is the bandwidth of the signal, right? Now I am wasting 2 f's of m. That's not needed. Okay, I'm just, bandwidth in RF is very, very precious. Okay, very, 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 useful to send more data. So I'm wasting the spectrum. So what can we do about it? Right? What is our solution? Our solution is single sideband modulation. Again, remember, all these things are theoretical, right? What we study in the textbooks. Okay, just keep in mind, these are all the textbook representations. And in the later down the road, I'm going to show you what will happen in the reality. Okay, so that's what keep in mind. It's in all textbooks. And single sideband modulation, same signal, baseband signal. I send it through a mixer, and I either keep the lower sideband or upper sideband. I can keep the lower sideband or upper sideband. Okay, contrast with this, check with this. So in this one, DSBSC, I have both lower sideband and upper sideband. In SSB, either I keep this guy or this guy. Okay, if I keep the lower sideband, it'll look like this, and upper sideband, it'll look like this. Okay, so, you know, what are some of the advantages? It's very easy, efficient to use of the spectrum and the power, because we're only sending half the spectrum now. And what are some of the disadvantages? Very high cost of the equipment. It needs a very sophisticated signal processing and transmitter to RX synchronization and a lot of other problems. Okay, and here are some of the equations: LSB and lower sideband and upper sideband. So see, what I'm trying to say here is the upper sideband here is completely gone. It is zero here. We don't even see it. Here, the lower sideband is gone. It is zero here. We don't even see it. This is what our textbook tells us via these equations. But is that the case in reality? Is that what really happens? Okay, we're going to find out. Okay, but how do somebody implement this single sideband modulation? Okay, I said it can be implemented using direct upconversion transmitter. You know, this is a schematic of how somebody would represent it. Okay, in a textbook mathematically, right? So we take the baseband, and then we you know, the cosine part of the baseband goes through here. The baseband is assumed to be complex. Okay, it has a real part and the imaginary part. So the real part is called I channel. Imaginary part is called Q channel. It goes through the I channel goes here, and the Q channel goes here, and this is the mixer, right? The mixer actually, what it does is it'll generate a signal at cos 2 pi FC, FC for carrier, frequency of the carrier, and then 90-degree phase shift and sine FC. And you take these two things, you multiply them, and you take these two things and multiply them and add them. Okay, basically we are trying to implement this equation here. We're trying to implement this equation, right? Actually, sorry, upper sideband. We're trying to implement this equation. Okay, the one in the bottom. Okay, there's a plus here, minus here. So, and then this is how one would implement that. Okay, in a textbook. Okay, remember that. And we have a local oscillator. We have a 90-degree phase shift. So the local oscillator is very precise. It's producing the signal at f sub c. And the cosine here of the local oscillator is going through exactly 90-degree phase shift to get the sine. And then we're implementing it. So everything is good, right? I mean, now I think we should maybe stop the webinar and just go home. But no, hold on a second. That's not why I'm here. Let's take a look at it. You know, oh, if everything works as expected, if everything is so perfect, then why am I even here? Why did Dr. Kamraz invite me to a webinar? And that's where the fun part begins, actually. So we know, going back to our trigonometric identities, a sub cos square something plus a sub sine square something is a. We know this, right? It's very simple. However, think of this. Here we are assuming that we have exact 90-degree phase shift in a textbook. But is it possible in reality? When I take a carrier and wanted to do 90-degree phase shift, do I really get a 90-degree phase shift? We are implementing using the semiconductors, right? So is it possible? What is going to happen to this equation if I have some kind of phase shift? Okay, what is going to happen? Okay, so that's where, you know, that's what I'm talking about, an ideal transmitter. Okay, this is an ideal direct upconversion transmitter. What is going to happen? The gains in phase and quadrilateral phase are ideal. The in phase and quadrilateral phases are exactly 90 degrees apart. Perfect input to output isolation. What does that mean? This is exactly 90 degrees. This I channel and Q channel are exactly 90 degrees apart. This LO is not, you know, is working perfectly. Okay, and the frequency of the LO, local oscillator, is very precise. The phase of the local oscillator is not moving. There are no DC offset. Okay, so these are all the ideal transmitters we design.
I request you to mute yourself.
So can we design such an ideal transmitter? Is it possible? Unfortunately, in reality, no, we cannot design such an ideal transmitter. If there is an ideal transmitter is available, then I don't have a job. Okay, I don't have to work at Motorola and LightPoint, but that's not the case. Okay, let's look at what is the reality. Okay, this is the reality. This is a practical direct up conversion transmitter. So what happens is, again, just keep, this is the simplest and the theoretical transmitter. Okay, I will leave it on for a few seconds. And let's add where all the possible errors can happen. Okay, so same, I have the baseband. Okay, and then I'm sending it. Okay, I made modifications to this. So I have the local oscillator. It is supposed to be cos f sub c, exactly precise carrier frequency, but now it has a frequency error, f sub e. There is, again, we talked about in baseband system. I want to send the signal at 10 megahertz, the clock, but it's operating at 10.1 megahertz. So 0.1 megahertz is the error. The same thing here. The local oscillator has an error. Okay, that's called frequency error. It has a phase shift. That's called phase jitter. Okay, then when I want to actually transform that cos to sine, I'm not getting exactly 90-degree phase shift. I'm getting 90 degrees plus some theta. And then on top of it, this cosine term here, the LO has an amplitude of A, but by the time it goes through it, the amplitude becomes A plus some error. Okay, these are the, and then this carrier operates at a very, very high power in order to make the mixer very efficient. So this could be leaking into this branch also. Okay, this carrier, it could be leaking here, it could be leaking here. And then on top of it, this is supposed to be my data, right? This is supposed to be my data. However, it has an offset, DC offset. Means there is some kind of leakage of some kind at the DC voltage, right? And same as the Q channel. So the very simple equation that we have here, okay, and look at what happens to it in reality. This is the equation at the RF. Okay, makes sense? See how complicated it became. And then in here we said, oh, using this simple equation, I can get rid of the lower sideband. It is zero, exactly zero here. I can only keep the upper sideband, right? But look at what happened in the reality. I have upper sideband all right, but the lower sideband is still there. A small part of the lower sideband is also sitting in there. I call that unwanted lower sideband image. It is not needed, it is not required, it is not wanted, but it is still there. And on top of it, going back here, right, there is no carrier here, right? I mean, that's the whole point. When I say DSBSC, what I mean with double sideband suppressed carrier. This carrier frequency is not showing here. Okay, I am suppressing the carrier. And here also I'm suppressing the carrier, again, theoretically in the textbook. But when I came here, okay, the carrier is sitting in here because of the carrier that is on LO, local oscillator of the carrier. It is leaking in. It is leaking into the RF signal. So, and what's the problem of these things? For example, when the carrier is leaking, it is taking up some power from my transmitter. Okay, all the power should be here. But now there is some power on the LSB, some power in the carrier. So what's going to happen is, I don't know if you can see this thing, but if this is a 16 QAM modulation system, if I'm supposed to transmit the signal here, because of all these problems, my signal actually went here. I'm not sure if you can see it, but this plus is supposed to be the required signal, but it became this moved here instead in the constellation. And the difference between these two is the magnitude error. Okay, they call it EVM. EVM means error vector magnitude. So again, the summary, basically, the whole talk that we are having today revolves around this slide. In reality, even though I would like to have a system like this, in reality, that's not possible based on how much price I pay for the local oscillator, based on how much what kind of mixers do I have, what are the tolerances, all these errors get introduced at various stages. Okay, and you may ask, hey, why is it important that when I'm making a cell phone, why don't I put a very, 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 very precise local oscillator, very accurate local oscillator? Yeah, it's going to cost money, so what? It's going to be good, right? But think of this way. Let's say a local oscillator costs $1, okay? And then Apple makes 100 million phones, okay? So the cost of the local oscillator for 100 million phones is $100 million, right? Very simple. Now, let's say I wanted to purchase a very precise local oscillator for my phone. And now the cost of the part became, instead of $1, now it's $1.10. Okay, multiply that with 100 million phones. So the cost has become 110 million now. So that means I am spending $10 million more. And just now imagine this across Apple, Samsung, Motorola, all these different companies. So the cost of producing the phone is going to become higher. When the cost of producing the phone becomes higher, you think the cell phone maker is going to keep the cost to themselves? No, they're going to send the cost to the consumer. The consumer is going to pay the difference of the cost. Means the cost of the cell phone is going to be higher for the consumer. So again, the idea is, how do I optimize the cell phone production? How do I lower the cost of the phone while managing these errors? The key term is manage. We cannot avoid these errors. They're not possible. I could pay a lot more higher price for the different components, but the problem then is the cost of the cell phone is going to go up. Again, I'm using the word cell phone here. It could be a Wi-Fi chipset. It's a Bluetooth module. It could be anything wireless, as a matter of fact. Then I cannot pay extremely high price, and it's not possible. It doesn't make economical sense. It doesn't make business sense. So therefore, let me see what is the reasonable price I can pay for the parts, and then how do I manage these errors? Okay. Okay, these are some of the errors that I just discussed, but I put it in a summary here. The baseband offset. Okay, that's basically here. Okay, that's called the baseband offset. And the carrier frequency error. Okay, the carrier frequency error is this guy. And carrier phase jitter. That is, there is a phase component introduced here. Okay, in the carrier. IQ gain imbalance, IQ phase imbalance. Basically, the I side basically goes back here. A cos square theta plus A sin square theta is A. But in this case, okay, there is an A here, but here is not A anymore, it's a B. Okay, this is the gain imbalance. Means that there is a difference in the gain. The multiplication term is A here and B here. So this equation will not hold anymore. And then phase imbalance, supposed to be 2 pi of C here, 2 pi of C here, but now there is a theta. There's a phase imbalance. So now this equation is not simply going to result in A, but something else. So that's IQ and gain, IQ gain imbalance, IQ phase imbalance. Carrier feed through. Carrier feed through is this here, leaking in to this chains that is doing the multiplication or addition rather here. Okay, carrier feed through. And then all, again, what is the impact, right? What are the impairments and what is the impact? And then they all cause something called EVM, error vector magnitude, okay? Or it's a different way to measure the signal to noise ratio. So here is the EVM. This is the same thing here that I put it in a very small one, but I kind of amplified it. So I am transmitting the signal here, the plus, but because of all the all the issues that I discussed. Now it kind of this signal actually moved here, right? So then this is the error in the constellation. Okay, a better way to measure this. So this is where I'm transmitting, but this is what I received. So the difference between the transmitted and the received, the error, okay, is EVM. They call it error vector magnitude. This is the very basic measurement we all do in the communication systems, in all the cell phones, Wi-Fi devices, Bluetooth devices, whatever they are. Okay, so this is the basic measurement that will tell us how good a particular system implementation is, how good a up converter is, how good a local oscillator is, how good a mixer is. This is going to be a one measurement that's going to basically tell us. Okay, and I'm going to show some examples using our company product. Okay, what all this means. Okay, is almost perfect signal. Again, I'm using the word almost because even the perfect signal in reality is still not perfect. Let's go back here. I'm using exactly the same example here. Okay, so I got upper sideband and the lower sideband is not there. Okay, it's not there. But again, so this is the spectrum of our signal. This is the upper sideband. There's not supposed to be any lower sideband. We use a bunch of filters, but still I cannot really completely make it zero because there's still some signal here. By the way, this is the frequency on x-axis and the power spectral density on the y-axis. Okay, this is the spectrum of the transmitter signal, and this is the constellation, 256 quantum constellation. This is power, power versus time. What is the power of the signal with time? And this is some of the measurements, RF measurements we do on the signal. Okay. So this table here is pretty much what we calculate, okay, in the received signal. For example, power. What is the power of the signal in this particular example? Supposed to be almost perfect signal, minus 10 dBm power. Okay. The IQ offset. What is an IQ offset? The difference between these two, okay, is minus 81 dB. That's very, very small. The frequency offset. Frequency offset is frequency error. What is the frequency error? This one here. The frequency error. Okay. It's about minus 0.31 hertz. It's very, very small. Okay. And then DC leakage. How much of the signal is and LO leakage? Okay. Minus 85.35 dB. Means how much of the signal, the LO signal, is leaking in. Minus 85 dB is very, very, very low, right? And then EVM. EVM is, this is what I talked about, the error vector magnitude, okay? On this signal is around minus 48.8 dB. That's very good, very, very low EVM. EVM is pretty much, you can think of EVM as the inverse of the signal to noise ratio, inverse of the signal to noise ratio. Higher the signal to noise ratio, lower the EVM because it's inverse. They're inversely related. So a negative number, lower value, lowest, a biggest negative number rather is good measurement for EVM. Again, this is supposed to be a perfect signal. Okay, now let's add some impairments. Okay, I added a frequency of 1 kilohertz. Okay, you see this? I'm measuring it's very tough to see it. Basically, maybe I should have added a little bit more frequency error to actually show it. Okay, what will happen is if I have a frequency error, the spectrum is going to shift to the right or to the left, depending on how much frequency error. 1 kilohertz is very difficult to see because here this is about a 50 megahertz signal here. In the 50 megahertz signal, 1 kilohertz is very difficult to see. Maybe next time when I do the presentation, maybe I'll add more frequency error. But basically, in this signal, the only thing that we did was we added the frequency error, and we do the measurement of the frequency error. Okay, and then add DC offset. Okay, remember DC offset basically is going back here. I'm adding this DC here. The I component of the Q component of the signal has some DC in it, DC signal in it. Okay, and then we said if there's a DC leakage, that's going to cause some kind of unwanted signal to the carrier. This is a perfect signal. almost perfect signal. When I added the DC leakage, you see the carrier now, this little spike here. And here I measured minus 85 dB DC leakage. How much am I measuring here? Minus 13 dB, minus 13.8 dB. Okay, that's almost 70 dB higher. Okay. The problem is, the higher the signal is, that it's going to destroy it. Okay. And then IQ and gain phase imbalance. Okay, what is this? Let's go back here. This equation, I got the gain imbalance and I got the phase imbalance. Okay, and we said if I have something like that, then I have the upper sideband is going to leak into the lower sideband. Okay, unwanted image, right? Look at what happened here. So I'm supposed to transmit only this, but now I also has, okay, some leakage of this signal in here. And I think I have a wrong screenshot here. It's not supposed to be 0. This is a IQ imbalance and gain phase imbalance. It's supposed to be a number. That's not 0, but I got to fix that. I'm sorry about that. But basically, this signal is leaking in this one. Okay. So let's put all those things together. I'm going to add the frequency error. I can add the DC leakage. I can add the IQ imbalance, and look at the constellation of the signal. Before we see the constellation, this is supposed to be the transmitter signal, but now I have the signal leaking into this one image, and I have the LO leakage, and this is what I received. Remember what I transmitted. This is what I transmitted. Look at these dots here, 256 Quang constellation. All the nice dots that are very compact, and I can clearly tell what dot is from which dot, or which symbol point is which symbol point. But now what happened? Look at it. Now the constellation is smeared. The constellation has errors in it. Instead of having the dots, now I got blobs of dots. So it is possible this point might have become this point, or this point might have become this point, or this point might have become this point. That means there are symbol errors. When I have symbol errors, my data rate goes down. So when we, for example, when we're talking on the cell phone, when we say, oh, I'm not getting a proper signal, I'm going to drop the call, let me go out, that is nothing but you're getting symbol errors here. When you get the symbol errors, the wireless link is going to break down. When the wireless link breaks down, then the call is going to drop. One of the ways to take care of those things is reduce the symbol errors. Maybe we step outside, we go to the balcony, or we go to the daba, or whatever it is. So maybe, hopefully the received power is going to go up and some of the errors can be minimized. Okay, so these are the symbol errors. So what do we do? So what do a wireless engineer in a measurement industry do? So say, let's take an example, Apple, Samsung, whoever it is. Once they make a device, once they make a cell phone in the factory, they do all these measurements. What measurements? They do power, they do IQ offset, they calculate the frequency error, symbol error, EVM, okay, IQ imbalance, DC leakage. They calculate all these things at a different frequency channels, at different technologies, 2G, 3G, 4G, 5G, Bluetooth, Wi-Fi, just name it, whatever is the wireless, whatever is the band supported, what are the frequencies, they perform all these measurements on the device. Okay, once it's made in the factory, and then make necessary corrections to the calibration tables. What do I mean by that? Let's imagine you are trying. Okay, calibration. What is calibration? I think I should probably say a little bit about that. Calibration is nothing but I'm driving my car, and the speedometer is showing I am going at 100 kilometers an hour. How do we know the car is actually going at 100 kilometers an hour? Maybe it's going at 90 kilometers an hour. Maybe it's going at 150 kilometers an hour. How do we know it's actually going at 100 kilometers an hour when we look at the speedometer? That's where the calibration comes into picture. What the car maker is going to do is, they're going to put the speedometer, they're going to put the car, again, I'm giving a very hypothetical example here, okay? Let's say they run the car at 100 kilometers an hour and see where the speedometer reading moves. And they put a dot there saying that, okay, the speedometer needle were to go here, that means it's 100 kilometers an hour. and then they go at 90 kilometers an hour, see where the speedometer reading is, or where the needle moves. There they mark it saying there's 90 kilometers an hour, and 80, 70, 60, 50, like that, they mark the needle, okay, the position of the needle. And that is how we know when we're driving the car, we know we're going at 100 or 90 or 50 or whatever it is. That's what the calibration is, okay? Calibration basically is taking a device and then calibrating against a standard. A different way to say it is in a cell phone, we get 1 bar, 2 bars of the signal, 3 bars of the signal, 4 bars of the signal. How do we know? How do we know the signal is better? Who is really doing this thing? Calibration does that. What it does is it puts a known signal into the cell phone and measures it and says that, okay, if it is like a speedometer, okay, if the signal is this much power, then display 1 bar. If the signal is this much power, display 2 bars. That's what the calibration is. So what do we do? So once, now that we discussed what calibration is, so I'm going to measure the frequency error. I saw 1 kilohertz of frequency error here, okay? So what I'm going to do is I'm going to go back here. I see 1 kilohertz of frequency error. So I'm going to tell my calibration tables, if somebody were to transmit the signal at this frequency, I am seeing 1 kilohertz of frequency error. So what I'm going to do is, instead of transmitting at f sub c, I'm going to transmit 1 kilohertz less. I'm going to transmit the signal at 1 kilohertz less. Because it has a 1 kilohertz of frequency error, this plus this is going to become whatever is the final frequency. It's like, again, I'm taking the example of a car. Let's say my car speedometer has a 10 kilometers an hour error. Means if I'm going at 100, it's going to show me I'm going at 110. So if I want to maintain, again, making it very simple, if I want to maintain 70 kilometers an hour speed, at what speed I have to go? I have to go at 80 kilometers an hour, because I know there is a 10 kilometers an hour error in it, okay? So if I go at 80 on the speedometer reading, I'm actually going at 70. I know it's a little confusing, but I'm really hoping that you're following me here. So I just gave an example using the frequency error. So they make the necessary correction to the calibration tables and they redo the measurements. Once I fix the frequency error in the calibration tables, I redo the measurements and go back to estimate the impairments. And hopefully this time I'm not going to see 1 kilohertz frequency error, but I'm going to see a little less than that, or maybe very close to 0 frequency error. Like that, I do the measurements on all these different factors, different impairments, and then I fix them one by one. So make sure that the impairments are within the limits as specified in the wireless standards. We cannot make the impairments 0. The frequency error cannot be made 0. It's impossible in reality. But what I can do is I can make it as low as possible and less than the limits specified in the wireless standard. For example, the wireless standard may say, okay, the frequency error should not be more than 500 hertz. And then I'm going to make the necessary adjustments so that my frequency error is, less than 500 hertz. Okay. So like I said, one can never make the impairments go away, but what we can do is we can minimize them. So all these problems that we see here, this carrier leakage, frequency error, or phase imbalance, phase imbalance, or gain imbalance, or anything, we cannot get rid of all these impairments. We cannot make this guy 0. Okay. While the textbooks and the theory and everything says that we do not consider all these things at all. However, in reality, all these are present. We cannot make them 0. But what we can do is we can minimize them. We can make the impact of these impairments as low as possible so that this LSB is going to become a lot lower. The carrier is going to become a lot lower. Okay. That is the job of a wireless engineer in the measurement industry. Okay, that's what we try to do. Okay, so that a component that is purchased at $1 can still be operated without increasing the cost of the manufacturing, without increasing the cost of the cell phone. So somebody makes a cell phone in the design phase or a prototype, they will bring it to us. Then we look at the prototype and then we make all these measurements. And then we're going to say, hey, You have a problem with the frequency error. You have a problem with the phase error. You have a problem with IQ imbalance. You have a problem with the gain imbalance. After all this measurements are taken, once we report it to the customer, so what we're going to do is the customer is going to make the necessary changes in their hardware design. Once the necessary changes are done, once they think that, okay, this is the best I can do, and then we will take that and then we will provide the measurements, calibration algorithms, and make the device such that it meets the wireless standards and also standards set by the government. Okay. For example, if the cell phone is supposed to transmit at, say, 20 dBm power, the government says that, okay, I am going to allow the cell phones, however, they cannot transmit more than 20 dBm of power for whatever the reasons are. Every country has their own wireless mandates. But if the cell phone is transmitting at 40 dBm power, that's violating the government requirements. Forget the wireless standard. So that means that somebody on the government side can measure and say that this cell phone is not meeting the standards set by the government of India, and they can ban the phone from being sold in India until they fix the problem. So what do? Again, we not only take care of the wireless standards requirements, we also take care of the government standards requirements, and then we will provide the feedback to the customers until the phone is taken into the manufacturing phase. Once the phone is in manufacturing, the components in every phone are different. They have different tolerance limits, different manufacturing conditions. So we do these measurements on every phone. If there are 100 million phones are made, we make all the measurements on all the 100 million phones, and then we let the customer know what phone passed the wireless standards, what phone passed the government standards, and what phones failed them, and then they're going to go and figure them out. Okay, so basically, if I go back here, I'm not sure if you can see my screen here on the light point. That's what these products do. I hope I am tying the knots. I mean, connecting the dots rather. So all these tests, these are called wireless testers. They are deployed. For example, this one, IQ Extreme M, it is in a high volume smartphone test. Okay, just an example. This is for Wi-Fi. This is for IoT. This is for millimeter wave. So what these guys are going to do, you take this tester and you put it in the factory lines. There are hundreds and thousands of these kind of testers in factory lines in Asia, in China, Taiwan, Korea, wherever it is. And each of these testers, I mean, the cell phones, they go through these testers, make sure that all these requirements are met, and make a cell phone pass or fail, and then it moves on. Okay, what is the summary? SSB is used to reduce the bandwidth and power requirements. Ideal SSB requires perfect synchronization of the TX and RX. But in reality, it is not possible to have a perfect TX and RX because of the component tolerances, PCB layout, manufacturing process, etc., etc. So it's not bad to have the impairments as long as they can be measured and controlled. Okay, it's not bad to have. Okay. And RF measurements are used to measure these impairments and calibrate the wireless devices. And once we calibrate them, we measure the impairments again as within the limits specified by the wireless standard. Okay, I think that pretty much does it. I hope you did learn something about what we do. And then if anybody has any further questions, and they can reach out to Dr. Kamaraju, and he's going to relay the questions to me. And then again, if you let me see, if you were to 1 second. Okay, here. This is our LightPoint website. Okay. This is my company website, www.company.com, sorry, lightpoint.com. And you can see there, for example, you can go to the products. Okay, you can look at this product, for example, IQ Gig 5G, what are all the different things it does. You can, basically all the different measurements it does, and you can look at the technical specifications. Okay, if you're interested, and you could try to study more. Okay, and so on and so forth. Okay, and so basically, this is by no means a complete RF measurements and you know what happens, but this is just a start, a start for people to understand what goes on in reality, and what we as wireless engineers do, and then how some of the practical manufacturing process are different from the theoretical things that we read in the textbook, and then what should happen if a device were to come in with some tolerance issues or component issues and stuff like that. So I hope this gives you some kind of background to at least look forward to what we do in the wireless area. Thank you very much, and now I can take some questions if may I have any. And you may mute your microphone and ask the question, and I kindly request to unmute it. Sorry, you can unmute your microphone, ask the question, and then please mute it once you're done. Thank you.
Hello.
Yes.
I request all the participants who want to interact with you, who want to interact with the speaker. So you may unmute either video or maybe the audio. Our speaker, Dr. Y. Ramakrishna Garu, ready to answer it.
Sir, good evening, sir. My name is Anil Kumar. Sir, audible?
Yes.
Yes, audible. You may speak.
Sir, I am from Maricha Engineering College.
Okay.
Sir, in slide number 2, actually modulation means it converts a baseband signal into passband signal or RF signal, right, sir? But but in slide number 2.
Okay, hold on. Let me go to slide number 2. 1 second, please. 1 second.
Slide number 2. After coding, there is a modulation, sir.
This slide?
Yes, sir. Yes, sir.
Okay.
After coding, there is a modulator. So modulator converts a baseband signal into passband signal, right? But the baseband communication system, in baseband communication system, we are using a modulator to do the modulation, sir. I have a doubt.
Yeah, so modulation actually, so it's again that's where some of the disconnect between the textbooks and the reality. So modulation here is not a conversion. Okay, modulation here is taking a 0-1 data bit streams, okay, zeros and ones, and convert that into either QPSK 16 QAM or BPSK 64 QAM or 256 QAM. Okay.
It's mapping in communication.
Exactly. It's exactly modulation mapping. Let me put it. That's a very good word to use. It's modulation mapping. Okay. Whereas actual conversion to passband, that is what is called mixing. Okay. It's called actually mixing. So if you can
doing two modulations in RF communication system. One is mapping. Another one is higher order modulations, and not higher order modulations. I mean OFDM, FDMA.
Okay.
Like that.
The OFDM and FDMA is all done here.
Here, starting second blocks, na, sir?
Right, correct. It's modulation. So for example, this modulation, this part does the mapping, OFDMA and all the stuff like that. The mixing is, it doesn't matter whether we use OFDMA or WCDMA or GSM. This mixing is the same. It's just up conversion, converting from one frequency to a different frequency, and like what you said, passband, so basically that's why in industry this is called modulation or modulation mapping, and this is called mixing. Okay, up conversion and down conversion. Make sense?
Okay, sir. Thank you, sir. Thank you for clarifying the doubt.
You're welcome.
Thank you, Andy. Thank you. From Aditya Engineering College. Thank you. Any participant?
Hello.
Yes.
Sir, మాట్లాడండి.
Good evening, sir. This is Ramana Reddy from Nalanda Institute of Engineering and Technology, sir, Sattanapalli.
Hello, sir.
Welcome,
How are you?
sir. Welcome, sir.
Very nice session and informative session, sir. Wonderful PPTs. And thanks to the management also, sir, GEC. Very nice session, sir. And also thanks to organizers. Thank you very much, sir. Nice session.
Thank you, Ramana Reddy garu.
Anybody has any other questions? Or did you type anything in the chat that I should go through? Any questions were typed in the chat?
Maybe there is no questions in the chat box. Just most of things, there is a positive feedback, and they're introducing themselves. If any,
you may ask any questions you know that you have. You know, it doesn't matter what the question is. Feel free, and don't be worried about the question. You know, as always, we learn from each other all the time. So please feel free to ask any questions you may have.
Hello.
Yes.
Namaste, sir. This is Ramakrishna from Goodlower Engineering College.
Namaste, sir.
Sir, in a smartphone, there are different antennas working for different purposes, like FM, like Wi-Fi, Bluetooth. There are different antennas.
Yes.
Of course, they are all working at different frequencies.
Correct.
Are there any chance of interference or other impairments? Of course, they are working at different frequencies. There is no chance of interference. But how all these antennas are interlinked to do simultaneously?
It's a very good question, actually. You're absolutely correct. So basically what happens is the antenna layouts, for example, for Wi-Fi, for Bluetooth, for cellular communication, they are different antennas, actually. Okay, a typical cell phone will have at least 3 antennas, one for Wi-Fi, Bluetooth, a GPS Bluetooth, one for Wi-Fi and one for cellular. And then more sophisticated cell phones has a lot more antennas. Okay, so there is always a leakage between one antenna to another antenna because of the PCB layout and the proximity and the frequencies that are operating. So what we do is, to address exactly the problem that you're talking about, for example, they turn on the Wi-Fi, okay, and then they transmit and they do the measurements on the cellular antenna, okay, and see if there is any interference of any kind, okay, and or maybe they turn on the cell phone antenna and they measure their Wi-Fi performance to see if there is any interference. Okay, and so basically what they do is they do all these different combinations, Wi-Fi, Bluetooth, cell phone, and all these different antenna combinations, and they try to figure out if there's any interference. And most of the time, what they do is all these calculations and measurements are done during the prototyping. And they typically have a prototype 1, prototype 2, and so on and so forth. But by the time the manufacturing or final production is done, most of the interferences are, hopefully minimized in the design, in hardware design. And then, and then finally, they would what they would do is that they would do the measurement in the final device anyway at the time of manufacturing, just to confirm and make sure that the interference is minimized. Did I answer your question?
Sir. Yes, sir. Thank you, sir.
Yeah, thank you.
Sir, this is audible?
Yes, please.
Audible, sir.
Sir,
Please
what is the advantage of if the carrier is suppressed, or we having any disadvantage? Carrier, sir.
Yeah. Sure. So let me share that.
Because in vestigial sideband, some of the carrier will be there and have learned, sir. But as compared to the DSB-SC and single sideband, here all the above 3, the VSB is more advantage, they are saying.
Right. So
can you clarify me about this?
Absolutely. Again, very good question. Okay, like you said, VSB, right? Vestigial sideband, and there is a carrier present. Okay, the application is very different. For example, typically VSB is used for the TV communications, right? I mean, you
yes,
have one transmitter sitting in, I don't know, somewhere, and then you have millions and millions and millions and millions of TVs, okay, or even billions of TVs in the world, right? So typically the The point there is, our expectation there is to keep the cost of the TVs to as low as possible, right? For example, in the US, I can go and buy a TV for about $50, right? $50 is I don't know, it's about 3,500 rupees, right? The point is, so I cannot afford to have. Okay, if you go back to my slide here, single side. I don't know if you can see my slides here. In SSB, the disadvantage
I can see, sir.
High cost of the equipment, sophisticated signal processing, and TX RX synchronization. Main point, TX RX synchronization, right? So that means, what is the reason for the high cost of equipment? You got to do very high signal processing, and there should be TX and RX synchronization. That means the TVs that I have to be produced at a very high cost because of the more signal processing and more sophisticated synchronization because of the oscillators and everything that are inside. So how can I keep the price of the TV lower? I could, for example, send the carrier so that I can eliminate the TX-RX synchronization and the sophisticated signal processing. That the TV is going to look at the carrier, it exactly knows what's the frequency error, what is how to do the synchronization, because the carrier is present all the time and the TV is only receiving, okay, it's not transmitting anything, right? There's only one transmitter and there are millions and millions of receivers. Whereas in a cell phone, it is not the case, okay? Cell phone, is a transmitting as well as the receiving. When you transmit something that has a carrier present, okay, when you're transmitting something that has a carrier present, that means you're wasting the transmit power, right? You're wasting the power, because in order to increase the signal of the upper sideband, because some of the signal is going into the carrier, you got to transmit at higher power. When you transmit at a higher power, the cell phone battery is going to be used even higher. So the applications are very different. Therefore, in a cell phone, it is bad, as a matter of fact, in order to have the carrier, because it's doing two things: increasing the power of the transmitter, it is decreasing the battery life, and also it is causing a lot of other interference issues. So, and there are more, therefore the idea is, do not transmit it by increasing the signal processing. Yeah, the cost is going to be higher, but again, the difference between cost of a TV versus the cost of a cell phone, okay, the economics and all, they drive it. Did I answer your question?
Hello, Rajesh Kumar garu, please participants request you to, before ask the question, please introduce yourself.
Okay, sir. Sir, this is Rajesh Kumar, assistant professor from Dr. Lankapalli Bullai College of Engineering, sir.
Okay,
thank you, sir. Thank you, Rajesh Kumar garu.
Thank you, sir. Thank you for the answer.
Please ask your question.
Participants, before asking the question, please introduce yourself.
So, Dr. Rajesh, what is your question?
Sir, my question is completed, sir.
Oh, okay. Very good.
Thank you.
I hope I answered.
Thank you, sir.
Okay, thank you.
Yes, sir. Yes, sir.
Okay.
Thank you.
Please, please mute yourself.
Any other questions, participants? Okay, I hope then the Q&A is done. Looks like there's no further questions. Again, if you have any questions or anything, you can always reach out to Dr. Kamaraju, and he's going to relay any questions or any other clarifications that may be needed, and then I will communicate with him. And I would like to hereby take this opportunity to thank GEC College of Engineering for providing me opportunity to speak a little bit about my experiences and my background and some of the work I do, and also the participants for all the questions, and also my special thanks to my very good friend Dr. Kamaraju for the invitation and giving me an opportunity to speak about some of the work I do. Thank you very much, and have a good night.
Okay, just a the vote of thanks. Anyone wants to? Okay, before going to close the session, just normally the vote of thanks. For this session in the inaugural, our thanks to our principal Dr. P. Ravindra Babu Garu for giving addressing our participants. Principal academics Dr. B.S.N.R.V. Prasad Garu. I also thank our another vice principal administration Dr. P. Karuna Kumar Garu and my friend head of the department Dr. V.V.K. Prasad Garu. And one of the colleagues, Vishendra Babu, is operating in the background, arrange all this event. And banner and welcome preparation and the decorations by Sri Kushal Chandra. And finally, our many special thanks to today's speaker, Dr. Y. Ramakrishna. Because of we are looking for a long time, so we want to hear your talk. Fortunately or unfortunately, due to the COVID, we got an opportunity to hear your talk. I thank Dr. Y. Ramakrishna Garu accepted our request and delivered talk today. And I thank all our GEC faculty, and I thank all the participants. Nearly 25 engineering colleges are participated in this event, excluding our Goodlovaler Engineering College. I hope this talk may be much useful for you. And coming days, we want to conduct one workshop, that is a faculty development program, maybe the 1 week program. So mostly that is related to the VLSI and related to the embedded systems, related to the IoT and communications. We are expecting this FDP program purely by the industry people. In industry, abroad as well as in India, so we are requesting them shortly we come with very good program. I hope this session may be ended. I thank all the participants for active participation and listening. And one more thing, we are giving a link in the chat box. If you submit your feedback form, immediately you get the certificate. Don't forget this one. Dr. V.V.K. Prasad Garu, you want to speak anything on this?
Nothing, sir. Once again, I am very much thankful to our resource person, Dr. Y. Ramakrishna Garu. Sir, thank you very much, sir, on the behalf of EC department. And I am looking towards such a cooperation future also from you, sir. Thank you very much, sir, for your excellent presentation.
Thank you, sir. Thank you very much.
Thank you, sir.
Ramakrishna Garu is a best friend to me.
Yes, sir. Yes, sir.
Very simple man and humble man also.
Sir, whenever he comes to India, we will invite him to our college, sir, once.
Yes, yes.
Definitely. Thank you.
Yes, sir.
Thank you. Any participants what they want to speak? From GEC, only Dr. Y. Ramakrishna is asked. Any other participants from GEC or outside of the institution? Anyone? Or not only question, they want to give any feedback, then you may give in the live session. We're all engineers, no worry.
Hello.
Sir, Chappan, sir, Ramakrishna Garu.
Sir, we would like to arrange a 2-week faculty development program during the month of November or December on millimetric waves.
Oh.
It is an FDP sanctioned by AICT and ISTE. We would like to get valuable inputs from Dr. Y. Ramakrishna Garu, who has given the webinar right now.
So Dr. Y. Ramakrishna is requesting Dr. Y. Ramakrishna Garu.
Very interesting. Yeah, we actually we do quite a bit of work in the millimeter wave, and you know, I think some of the products that I showed you, actually the products I showed you on our website, that's actually a millimeter wave product. It's a very interesting area, and a lot of new challenges, because we're talking about operating in gigahertz of frequencies. Most of the theory and practice that we knew in the lower frequency range doesn't hold anymore. There are quite a bit of different challenges of their own in millimeter wave measurements and testing. So when time comes, definitely we can discuss such a possibility, Dr. Ramakrishna.
Thank you.
Thank you, sir. Thank you very much.
Anyone who belongs to communications research group? Anyone wants to speak? From Department of ECA Communication Research Group or Signal Processing Research Group? Sir, in our department there is 3 groups are there. VLSI Design and Embedded System Group, and Signal Processing Group, and Communication Research Group. Young faculty, come forward to give feedback. Rajesh Kumar garu మాట్లాడండి.
Hello, sir.
మాట్లాడండి.
Sir Ramakrishna garu, sir.
చెప్పండి చెప్పండి.
Yeah, I can hear you. Please go. Yeah, I can hear you.
Sir, this was a wonderful session I was attending, sir, from the last 10 to 20 days.
Very good.
Whatever which was given, it is a very valid information, sir, and it was useful for me also for the future, for any research work. Thank you, sir. Thank you for this useful information, sir.
Thank you, Rajesh Kumar garu.
Thank you, sir.
Thank you very much, sir.
Anyone? They want to give feedback? Anyone from Communication Research Group? Shendra Babu garu, please put the link for feedback form.
Yes, sir. I did that.
Okay.
That, sir. I got responses also, sir.
Okay, very good, very good.
It's done, sir. I think it's done, sir. Can we close it? I think.
Okay, shall we close?
No one is responding. That's
okay, right.
Okay. Good night. Bye bye.
Okay, thank you, Ramakrishna.
Okay.
I'm so happy today after hearing your wonderful talk.
Thank you. Okay.
Thank you.
Thank you, Dr. Prasad.
All the participants.
Thank you, sir. Thank you, sir.